Welcome back and thank you for drifting into the quiet side of the night. Tonight's story follows a starship chasing a single beam of light and discovers why the universe will never let it catch up. Time slows, mass grows heavier, space itself turns hostile, and the cosmic speed limit stands unbroken. If these calm journeys through deep space help you relax, please gently like this video, subscribe, and tell in the comments where in the world you're listening from. In the quiet hours of the night, a familiar dream unfolds in countless minds, a fragile craft gliding effortlessly between stars, leaping from world to world, as if the distances were nothing more than gentle steps across a darkened room. The planets of the home system drift past like lanterns on a slow river. Then the ship veers outwards, slipping beyond the comforting glow of the local star, into the vast and speckled gulf. In this vision, travel is simple. Engines hum softly, horizons bend, and the next sun waits only a short journey away. It feels natural to imagine that one day this will be routine, that the universe is merely waiting for the right machines to arrive. Yet within this comforting picture, an invisible line already lies drawn across the fabric of reality. Long before any species builds its first rocket, the cosmos has set a speed that nothing with mass may ever reach. The dream that seemed wide open rests inside a cage whose bars are woven from space and time themselves. The speed of light, that pale beam that crosses a room in a whisper of an instant, is not simply fast, it is final. In everyday life it seems almost irrelevant. No one notices light moving from wall to wall or from screen to eye. Shadows shift, reflections glint, and the glow of the star at the center of the system bathes a small planet in a steady blaze. It is easy to believe that this brightness arrives everywhere at once, that illumination is essentially instant. Only careful minds watching the heavens with patience discover that the beam has a pace, that even light must take its time between one place and another. Over centuries, observations refine that pace until it becomes a single stubborn figure, roughly 300,000 kilometers per second through empty space. At first, this number appears to be just another measurement, like the height of a mountain or the mass of a planet. But hidden inside it is a rule that applies everywhere to every event in every corner of the observable universe. No material object, no signal, no whisper of causality itself may outrun that beam. The universe behaves as though this speed is a boundary written into its most basic blueprint. In the imagined starship, acceleration begins innocently. Engines push, fuel burns, and velocity climbs. At 10,000 kilometers per hour, the craft is quick on a planetary scale. At 100,000 kilometers per hour, it is already beyond anything ordinary. As the ship presses harder and the calculations extend into regimes seldom glimpsed in daily life, something subtle starts to happen. The arithmetic of ordinary motion no longer holds. The relationship between force, mass, and speed begins to twist. Far from planets and familiar air, the craft approaches a domain where the rules of Newtonian intuition quietly give way to a deeper order. In that deeper order, laid out by the equations of relativity, the speed of light is not just a convenient reference. It is a limit built into the geometry of space-time. If the ship could see its own future mapped as a path, every possible line that respects cause and effect would lean beneath that ultimate slope. Any attempt to draw a steeper path, one that would correspond to travel faster than light, simply fails to fit within the fabric. The universe does not merely resist such motion, it does not even allow a consistent description of it without tearing logic apart. The quiet stars that seem so inviting in the night sky become markers of unreachable haste. Even before considerations of fuel engineering or biological endurance enter the story, the mathematics has already sealed off certain possibilities. No matter how powerful an engine becomes, no matter how advanced a civilization grows, a ship with mass cannot be plotted along a path that crosses that bright boundary. It may approach the line ever more closely, shaving away the difference with immense effort, but the limit itself recedes like a horizon that always lies just beyond the next ascent. A paradoxical image emerges. On the one hand, the cosmos appears open and expansive, scattered with galaxies, clusters, and filaments stretching across scales that defy ordinary comprehension. On the other, there exists an uncompromising speed that silently governs what journeys are even conceivable. Between nearby worlds, that limit seems permissive, allowing probes and craft to move at tiny fractions of the cosmic maximum. But as attention turns outward toward neighboring stars and beyond, the same limit hardens into a wall. Distances measured in light years reveal what the phrase truly means: the time a beam of light requires to cross the gulf. For matter, that time is a floor that can be approached but never undercut. This realization changes the dream. The starship still flies, its hull still gleams softly in starlight, yet its path through the galaxy can now be traced only within a narrow band of possibilities. There is no sudden leap that carries it across thousands of light years in a single lifetime. There is only patient motion at some fraction of the ultimate speed, with all the consequences that such slowness implies. Time aboard the ship may bend and stretch in strange ways, but the underlying boundary remains unbroken. In the calm darkness, the speed of light stands revealed not as an arbitrary technical detail, but as a cosmic commandment. From this starting point, every hope of faster travel, every proposal for exotic engines, and every whisper of shortcuts through warped space must contend with that single stubborn limit that defines how quickly cause can touch effect anywhere in the universe. In earlier ages, before clocks ticked with the precision of atoms, and before lenses carved sharp images from starlight, light itself felt like an immediate presence. Flames were kindled and rooms awakened in a single breath. The star at the center of the system rose above the horizon, and landscapes brightened without any sense of delay. In this older imagination, light was not a traveler at all. It was a condition of things, a simple property that arrived everywhere at once. Philosophers debated the nature of illumination, wondering whether it consisted of particles rushing outward or a disturbance flowing through some hidden medium, but very few seriously suspected that it could be slow enough to measure. The cosmos seemed too vast, and the beam too swift for any human device to catch it in transit. The first hints that light might move with a finite speed came not from laboratories but from the sky itself. As telescopes improved and observers turned their attention to the restless moons of distant planets, a subtle inconsistency appeared in the heavens. A careful watcher tracking the eclipses of the small moons circling a giant world far beyond the orbit of the home planet noticed that the predicted times of disappearance and reappearance were not always accurate. Sometimes the events seemed late, sometimes early, with a pattern that matched the changing distance between the observing world and that distant planet along their paths around the central star. What looked at first like a nuisance in the data gradually resolved into a quiet revelation. If the timing of those distant shadows shifted with the separation between worlds, then something must be taking measurable time to cross the gap. That something was light. The idea was startling. If light required time to travel between planets, then perhaps it also required time to move from the central star to its orbiting worlds and from one end of a laboratory to another. The beam that seemed instantaneous in daily experience might be running on a cosmic clock. By comparing the deviations in the eclipse timings with the known changes in distance, the first rough estimate of the speed of light emerged. It was not exact, but it was finite, and the implications quietly rearranged the map of reality. Light joined the company of things that move, that depart from somewhere and arrive somewhere else after a measurable interval. It was no longer a simple, timeless presence. It was a traveler. As the centuries unfolded, curiosity turned inward from the motions of moons to more controlled experiments on Earth. Long corridors, rotating mirrors, and clever timing devices were brought into service. Beams were sent across valleys, bounced between distant reflectors, and chopped by spinning wheels whose teeth separated flashes into pulses. Each design tried to catch light in the act of crossing a known distance to convert its fleeting passage into numbers that instruments could record. Though the apparatus grew more refined, the goal remained the same: to pin down how fast this elusive traveler really moved. Results converged slowly but relentlessly. The speed was staggeringly high, far beyond any human or mechanical motion, yet always finite, always close to the same immense figure. Different methods, different laboratories, and different generations of experimenters all arrived at nearly identical values. The conclusion hardened. Light did not simply appear, it raced. It covered about 300,000 kilometers in each second across empty space. This consistency suggested something more than a mere property of a particular phenomenon. If every careful attempt to measure light's speed yielded the same value regardless of the color of the beam or the nature of the source, then perhaps this speed held a special status. It began to look less like an accident and more like a signature of the structure of nature itself. Meanwhile, another line of inquiry unfolded. As the 19th century advanced, the study of electricity and magnetism led to a unified description in which oscillating electric and magnetic fields could propagate as waves. The equations describing these waves predicted that they would travel at a specific speed determined by fundamental properties of the vacuum. When the calculated value was compared with the measured speed of light, the agreement was astonishing. It appeared that light, at least in its ordinary form, was an electromagnetic wave, a self-sustaining pattern of electric and magnetic fields moving through space at that special speed. This unification deepened the mystery rather than closing it. If light was an electromagnetic disturbance, and if its speed was fixed by constants that describe the vacuum, then that speed seemed to be woven into the very emptiness between things. It did not depend on the motion of the source in any simple way. A beam emitted from a moving lantern or from a stationary star appeared to rush outward with the same pace relative to the surrounding space. The question then shifted. If light had a definite speed in the vacuum relative to what was that speed defined, many thinkers imagined an invisible medium permeating the universe, a subtle substance through which electromagnetic waves rippled. In this picture, the measured speed of light would be its speed relative to that medium. A sufficiently careful experiment should detect motion through this cosmic ocean, revealing a slight difference in light's pace along different directions. Devices were built with precisely this aim. Beams were split, sent along perpendicular paths, reflected and recombined to look for tiny shifts in the interference patterns that would betray a change in relative speed. As Earth orbited the Sun, Any drift through the hypothetical medium should produce a gentle but measurable variation. The result was silence. No matter how the apparatus was rotated, no matter the time of year, no convincing shift appeared. The speed of light behaved as if it were the same in all directions and for all motions of the laboratory itself. The expected signal of motion through a background medium failed to materialize. Instead of clarifying the situation, this null result opened a deeper puzzle. If there were no detectable medium, and if light's speed remained stubbornly the same in all directions in an earth-bound laboratory that was clearly moving through space, then perhaps the assumption that speed simply added in the usual way needed to be questioned. Observers' sources and beams might not relate to one another through the simple arithmetic of everyday motion. The measured constancy of light speed, first hinted at by eclipses of distant moons, and then hammered into place by intricate experiments on Earth, now demanded a radical reinterpretation of space-time and motion themselves. The beam that once seemed like a simple instantaneous glow had become a precise messenger from the deep structure of the universe, insisting that something fundamental in old intuitions about velocity could no longer stand. The stage was set for a new view in which light speed was not just another number, but the hinge on which all measurements of time and distance would turn. In a modest office scattered with papers and diagrams, a quiet revolution begins to take shape. A young examiner of patents spends long days reviewing other people's inventions, while a different problem circles in his mind. Experiments insist that the speed of light is always the same, no matter how a source moves, no matter how an observer drifts through space. Devices built to detect motion through a hidden medium report nothing at all. The result is not noise but silence, a silence so consistent that it demands explanation. Instead of adding new mechanisms, the emerging theory removes assumptions, asking what reality looks like if the constancy of light is taken as a first principle rather than an odd exception. At the center of this new picture stand two simple statements. The laws of physics have the same form for every observer who moves at constant speed in a straight line. The speed of light in empty space has the same value for all such observers. On paper, these ideas look gentle and compact, yet they refuse to coexist with everyday intuition. If a source sends out a beam and an observer rushes toward it, common sense says that the measured speed should be larger. The experiments say it is not. The new framework chooses to trust the experiments completely and bends the rest of reality around them. The first thing to give way is the old idea of universal time. For centuries, time has been imagined as a single river flowing identically for all regardless of motion or place. In the new view that river fragments into many local streams, each observer carries clocks that tick according to that observer's motion. If the speed of light is to remain the same for all, then the rate at which those clocks advance cannot be universal. Ticking must slow or quicken depending on the path through space-time. Distance must yield as well. Measuring rods cannot hold the same length for all who look at them. A rod resting in one frame appears shortened to another frame that slides past at high speed along its length. Space and time, once treated as separate arenas, fuse into a single entity in which intervals of space and intervals of time transform into one another when observers compare notes. Equations called Lorentz transformations capture this strange choreography. They specify how coordinates of an event in one frame translate into coordinates in another frame moving at constant speed. Inside them lies a factor that depends on speed divided by the speed of light. At low speeds, this factor is so close to 1 that its influence is invisible. Cars, aircraft, and even the fastest present-day rockets move too slowly for the effect to stand out against ordinary noise. The world looks comfortably classical. As speed climbs toward a significant fraction of light's pace, the factor begins to grow. Time intervals in the moving frame stretch when viewed from outside. Clocks carried on fast craft fall behind clocks left at rest. Lengths along the direction of motion shrink. Two events that are simultaneous for one observer are no longer simultaneous for another who passes by. The firm sense of a single shared now dissolves into a patchwork of overlapping perspectives, all equally valid within space-time. Beneath this shifting surface, one quantity refuses to change. The speed of light in vacuum remains fixed for every inertial observer. The geometry of space-time leans and twists just enough in each frame to keep this number untouched. It becomes the fundamental tempo of the universe with the flow of time, the notion of distance and the ordering of events all adjusting themselves around it. Mass and energy, long treated as different kinds of quantity, also come together under the new rules. The equations say that even a resting object holds a store of energy tied directly to its mass. This rest energy does not depend on motion or temperature. It is a basic feature of matter. When the object begins to move, additional energy appears as kinetic energy. At low speeds, the familiar formula of classical mechanics describes this well. Near the speed of light, however, the total energy grows more quickly than that old expression predicts. The closer a body's speed comes to that of light, the more sharply its energy rises for each further gain in velocity. In practical terms, this means that energy invested in pushing a massive object to higher and higher speeds increasingly feeds its inertia rather than its motion. The object resists acceleration ever more strongly, not because of hidden friction or drag, but because the structure of space-time ties energy, mass, and motion together. Another long-held notion falls away in this framework, the idea of an absolute state of rest. There is no privileged backdrop, no cosmic platform that can be called truly stationary. Every constant speed frame is as good as any other for describing the laws of nature. Each observer carries a personal grid of space and time, yet the same equations apply in each grid, and the same speed of light sneaks into every description. The failure of earlier experiments to detect motion through an ether no longer looks like a disappointment. It becomes exactly what the new theory expects. There is no stationary medium for light to ripple through. Space-time itself is the stage, and its symmetry underlies the identical results seen by all inertial observers. As the new view of space-time settles into place, the Lorentz transformations stop being abstract symbols and begin to reveal a quiet structure that runs through every possible journey. Embedded in them is a single factor that measures how severely time and space must bend. When motion becomes extreme, a factor that sits almost unnoticed at ordinary speeds and then swells into something immense as velocity rises toward the universal limit. It is a simple ratio in spirit how fast an object moves compared to the speed of light. At walking pace, this ratio is so small that its square might as well be nothing. At the pace of a highway vehicle, it remains tiny. Even a swift aircraft or a spacecraft orbiting a planet carries such a small fraction of light speed that space-time barely shrugs. For these motions, the factor that governs relativistic effects hovers so close to 1 that no experiment outside a precision laboratory could detect the difference. Time appears universal, lengths appear fixed, and the classical picture remains a good approximation to reality. The change begins quietly when speeds reach a noticeable fraction of the cosmic maximum. Imagine a sequence of hypothetical journeys in deep space far from stars and planets, where only the geometry of space-time itself shapes events. A craft accelerates until its speed reaches 1/10 of the speed of light. The special factor that arises in the Lorentz transformations, the measure of deviation from classical behavior, differs from 1 by only a whisper. Clocks on board tick very slightly slower as seen from a calm frame, and lengths along the direction of motion shrink by a similarly tiny amount. For all practical purposes, the old rules still feel adequate. The wall ahead remains distant. Now the craft pushes harder, reaching half the speed of light. The ratio of its speed to light's speed is no longer negligible. The governing factor climbs above 1 in a way that can no longer be ignored. Time on board, as described from the original rest frame, slows by more than a trivial fraction. Processes that would take 1 year for an observer drifting in calm space take noticeably longer on the swiftly moving vessel when both sets of clocks are compared. Distances measured along the direction of travel shorten in the moving frame. The tapestry of space-time begins to show its relativistic weave. The climb continues. At 90% of the speed of light, the Lorentz factor has grown significantly. Time dilation now stretches intervals by more than a factor of 2. Events inside the craft seen from the original frame unfold at less than half the previous rate, while from the perspective of the crew, their own clocks remain normal, and it is the outside universe whose time appears distorted. Length contraction becomes dramatic. The distance to a target star measured along the direction of motion shrinks substantially in the traveler's frame. The geometry accommodates the unchanging speed of light by folding space and time more aggressively. When the journey approaches 99% of the speed of light, the quiet growth of the Lorentz factor turns into something more like a surge. A value that once sat near 1 has climbed to several times that. Time for the moving craft judged from the original rest frame runs more than 7 times slower. Processes that would take 1 year in one frame stretch beyond 7 years in the other. The path to the target narrows further in the traveler's coordinates, compressed into a fraction of its original length. Nothing physical has collapsed or broken. Rather, space-time has rebalanced its measures to maintain the constant speed of light for all observers. From here, each extra fragment of speed exacts a harsh price. At 99 9/10% of the speed of light, the Lorentz factor no longer counts in single digits. It rises into the 20s and beyond. Every attempt to shave away another small piece of difference between the ship's speed and the cosmic maximum multiplies that factor. Energy poured into acceleration translates less into added speed and more into an increase of this relativistic weight, this effective mass that resists further change. Time intervals stretch by tens of times when cross-compared between frames. Distances contract so strongly in the direction of motion that the universe seems to narrow into a thin corridor. The wall ahead becomes visible in the mathematics, if not in any physical structure. Plotting the Lorentz factor as a function of speed reveals a curve that slopes gently at first, then more steeply, and finally rises almost vertically as velocity nears the speed of light. No matter how close the speed comes to that limit, the factor remains finite yet grows without bound. At the exact speed of light, the expression would require dividing by zero in its hidden structure. The factor would leap to infinity, signaling that the framework cannot accommodate such motion for anything that carries mass. This is what the equations mean when they deny access to the ultimate speed. It is not simply that reaching that pace would be difficult. It is that approaching it sends the cost measured in energy and in distortions of time and space soaring toward infinity. The idea of mass plays a subtle role in this story. In the older, simpler view, mass is an unchanging measure of how much matter an object contains, a fixed property that does not depend on motion. In the relativistic picture, mass at rest remains constant, but the relation between total energy and motion introduces a new kind of inertia. As speed increases, the total energy grows with the Lorentz factor. The object behaves as if it were heavier in its resistance to further acceleration. Every new push must work against this effective increase. Near the speed of light, the extra energy required to gain even a tiny additional increment of speed becomes enormous. The wall takes shape here, as well as a region where energy requirements outstrip any plausible source. This interplay of factors turns the speed of light into a kind of asymptote. A traveler can aim ever closer to it, but no finite sequence of pushes will carry a massive object across that line. Unlike a physical barrier, which could in principle be broken or tunneled through with enough force, this wall is a feature of the underlying geometry. The equations that describe space-time simply do not produce a state where a massive object moves at light speed. They admit either speeds below that value for particles with mass, or speeds equal to that value for massless entities like photons with no continuous path that leads from one category into the other. Standing back from the mathematics, a strange landscape emerges. At the low hills of the curve, the everyday world unfolds where speeds are modest, and the relativistic factor rests near 1. Farther along lie the cliffs of high velocity where subtle effects become dominant and time and distance twist. Beyond that rises a vertical face that no traveler with mass can climb, where the Lorentz factor would become infinite and the energy demanded would exceed anything the universe can supply. The speed of light is not simply a fast pace, it is the crest of that impossible wall. This realization sets the tone for every later attempt to imagine journeys between the stars. Any blueprint for such travel must accept that as velocity rises, the universe responds by slowing time aboard the craft, compressing distances in the direction of motion and magnifying the effective inertia of the moving mass. The closer a path tries to draw to the light speed line on a space-time diagram, the more violently the Lorentz factor reacts. In that reaction, the cosmos quietly enforces its speed limit, turning a simple numerical value into an absolute boundary that reshapes time, space, and energy around it. In the emerging relativistic picture, mass no longer behaves as a quiet fixed quantity that simply sits inside equations. It begins to act instead like a living measure of resistance that swells as motion grows more extreme. In the calm world of slow speeds, this difference is invisible. A cart in a market, a train on its tracks, a satellite circling a planet all respond in ways that match familiar expectations. Push harder and the object accelerates in a straightforward way. Double the force and the rate of change in speed doubles as well. Mass seems to be nothing more than a constant that describes how stubbornly matter resists being moved. Yet the mathematics of relativity suggest that this stubbornness is not entirely fixed. At higher speeds, the total energy of a body becomes entangled with its inertia. Energy poured into motion begins to show up as an increase in the difficulty of pushing further rather than as a simple rise in speed. A helpful image appears in the mind, a cart rolling along a smooth floor. At first it is empty and almost weightless. A gentle push sends it gliding forward. As the journey continues unseen, hands place objects inside. Each new item makes the cart heavier, so each fresh push produces a smaller change in speed. Eventually, the cart carries such a load that the same effort barely speeds it up at all. In the relativistic story, there is no cargo being added, yet the effect is similar. The added energy itself, bound to mass by the deep relation between the two, behaves as if it were extra weight that the universe insists on counting. Consider a spacecraft drifting in interstellar space with its engines quiet. Its rest mass remains what its designers built, perhaps comparable to a large orbital station, thousands of tons of metal fuel and habitat. When the engines ignite, energy begins to flow into the ship's motion. At first, as long as the speed remains small compared to the speed of light, the familiar rule of classical mechanics describes the change well. The increase in kinetic energy matches the square of the speed and mass seems unaltered. But as the craft climbs toward a more serious fraction of light's pace, the relativistic relation between total energy and motion takes over. The total energy of the spacecraft, which includes both its rest energy and its kinetic energy, grows with the Lorentz factor. In practical terms, each increment of speed demands more energy than the last, not because of any external drag, but because that factor is rising. The ship behaves from the perspective of those attempting to accelerate it as if its inertia were increasing. A numerical picture clarifies the effect. When the craft reaches half the speed of light in some chosen frame, the Lorentz factor has risen modestly. The effective inertia is larger than the simple rest mass would suggest, but not by an overwhelming margin. Acceleration continues to be possible, though it already costs more energy per unit of speed than before. At 90% of the speed of light, the factor has more than doubled again. The same thrust that yielded a comfortable boost when the ship was moving slowly now produces only a smaller gain in speed. The craft resists change more than its rest mass alone would imply. If the engines are pushed to carry the ship to 99% of the speed of light, the factor has grown many times larger. Every attempt to close the remaining gap between this already immense pace and the ultimate limit demands a disproportionate investment of energy. The ship's effective inertia has swollen into something far beyond its static value. In this way, mass tries to chase light and finds that the road steepens with every step. The geometry of space-time responds to each new increment of speed by increasing the penalty for further acceleration. That penalty does not take the form of a visible barrier or an external force, but rather reveals itself in the ever larger amount of energy that must be supplied to achieve ever smaller improvements in velocity. The mountain ahead lengthens as the climber approaches the summit, its slope turning from gentle incline to nearly vertical cliff. In the limit where the speed would match that of light, the Lorentz factor would become infinite. The very notion of adding enough energy to reach such a state ceases to be meaningful. No finite supply can produce an infinite total. In this sense, the universe does not merely discourage attempts to reach light speed, it makes them undefined. The equations that govern motion refuse to describe a massive object traveling at that pace. There is no entry in the cosmic ledger for such a state. This relativistic swelling of inertia finds a mirror image in the realm of particles. In accelerators buried beneath fields and countryside, beams of tiny projectiles are pushed to speeds that skim the light speed limit. Each circuit around the ring adds a carefully measured amount of energy. At first, as the particles move from modest speeds to substantial fractions of light's pace, their velocity increases significantly with each injection of energy. Later, as their speeds approach the cosmic maximum, extra energy goes almost entirely into boosting the Lorentz factor rather than the raw speed. The particles become, from the viewpoint of the magnets that steer them, thousands of times more resistant to change than their rest masses would suggest, yet they still never quite reach the speed of light. They circle endlessly just beneath the limit, their effective inertia towering, while their additional gains in speed shrink to almost nothing. These observations are not mere curiosities of subatomic physics. They are direct evidence that the relativistic structure of mass and energy is real, not just a theoretical convenience. The same geometry that governs the motion of particles in a laboratory applies to any object of any size in any corner of the universe. A starship trying to attain nearly light speed would encounter the same hard law as a proton riding a magnetic field. As speed rises, mass in its effective form rises with it, and the cost of further acceleration grows without bound. This leaves a curious divide running through reality. On one side stand particles with mass able to move at any speed below the ultimate limit, but never to touch it. On the other side stand massless entities, such as photons, for which the equations themselves demand motion exactly at the speed of light and forbid any slower pace. There is no smooth path that carries matter from one category into the other. Mass cannot simply be shaved away by acceleration. A massive object can never be coaxed across the boundary by any sequence of pushes, because the cost of doing so diverges to infinity. When mass tries to chase light, it discovers that the gap it seeks to close is not merely large. It is of a different kind, a separation enforced by the very form of space-time's rules, ensuring that the realm of light and the realm of matter remain forever distinct. Time, which once seemed like a steady river flowing the same for all, begins to look different when motion nears the cosmic limit. In the quiet realm of everyday speeds, clocks agree almost perfectly. A pendulum in a small room, a quartz device on a table, and an atomic clock in an observatory all march forward together with only tiny deviations. It is tempting to imagine an invisible grid of universal timelines threading the universe and marking the same moment everywhere. Relativity quietly removes that grid. In its place, it offers a picture in which each path through space-time carries its own measure of duration, and in which the flow of time depends on how a world line leans through the fabric fixed by the speed of light. The new structure appears first as a feature of the Lorentz transformations. When one inertial frame examines another that glides by at constant speed, the equations show that intervals of time in the moving frame appear longer. A clock carried on a swift craft, when compared to one left at rest, falls behind. From the viewpoint of the original frame, the moving clock is slow. This time dilation is not a defect in the mechanism nor a sign of physical strain. It arises because the combination of space and time coordinates that keeps the speed of light the same for all observers forces those observers to disagree about how long events last unless they share exactly the same state of motion. At low velocities, this disagreement is almost unmeasurable. A spacecraft circling a planet at a few kilometers per second experiences a dilation so small that it would take many years for the difference to amount to even a fraction of a second. Yet as speeds increase, the effect grows. When a hypothetical vessel drifts at half the speed of light relative to some chosen frame, the Lorentz factor that governs time dilation already ensures that processes on board appear stretched compared to those in the calm frame. If the vessel could accelerate to 90% of light speed, its clocks as viewed from that frame would tick less than half as fast. A journey that feels like a few years to those on board would correspond to many more years having passed for distant observers who remained nearly at rest. Nature itself provides clear demonstrations of this elastic flow of duration. High above a planetary surface, energetic cosmic rays strike atoms in the thin atmosphere and create unstable particles known as muons. At rest, a muon survives for only a small fraction of a second before decaying into lighter components. If such particles were created without relativistic motion, almost none of them would be able to travel from the upper atmosphere down to the ground before vanishing. Yet detectors at the surface register a constant rain of muons from above. The only way to reconcile their short lifetime with the distance they cross is to note that they are born moving at speeds very close to the speed of light. In the frame of the planet, their internal clocks run slowly. From their own perspective, time passes normally, and they decay on schedule, but the thickness of the atmosphere in the direction of motion is length contracted. Two complementary descriptions, one in which lifetimes stretch and another in which distances shrink, both emerge naturally from the same relativistic geometry. A second confirmation orbits quietly overhead in satellites that carry precise clocks. Moving at several kilometers per second in regions of slightly weaker gravity than the surface below, they trace world lines along which time does not flow at the same rate as on the ground. Special relativity predicts that their speed should make their clocks run slow compared to clocks at rest, while the weaker gravity tends to make them run fast. When both effects are combined, the orbiting clocks advance by a small but significant amount more each day than identical clocks on the surface. Modern navigation systems must constantly correct for this difference. If they pretended that all clocks shared a universal rate, their position estimates would drift rapidly from meters to kilometers. Every successful fix on a map silently depends on the fact that time is not absolute. Thought experiments carry this elasticity of time into more dramatic territory. Two genetically identical individuals are born side by side on a planet. One remains at home living a life under the steady pull of local gravity. The other boards a craft capable of sustained relativistic flight and departs on a long loop around a distant star. On the ship clock's tick, work is done, and sleep follows wakefulness in an ordinary pattern. A certain number of years pass, and then the craft returns. When the siblings meet again and compare clocks, the asymmetry is unmistakable. The one who stayed behind has aged more. The world has moved on through a greater span of history. Technologies have advanced and landscapes have changed during an interval that felt to the traveler like a much shorter absence. The traveling path through space-time simply contains less proper time between departure and return than the path of the sibling who remained nearly at rest. This scenario is often described as a paradox, yet it hides no genuine contradiction. The two world lines are not equivalent. The traveler's path includes periods of acceleration and deceleration that break the symmetry with the stay-at-home sibling. When the geometry of space-time is taken seriously, the result becomes an inevitable consequence of how durations are assigned to different trajectories. Distinct paths between the same pair of events can contain different amounts of time. For near light speed travel, this dilation of time offers a kind of limited escape from the weight of cosmic distance. A crew able to endure extreme velocities could in principle cross many light years within a span of proper time that feels like a single human lifetime, because their onboard clocks would be dramatically slowed relative to distant frames. Yet this reprieve carries a quiet cost. While the travelers experience the journey as short, far more time passes in the wider universe. By the time they return, if they ever do, their original world may lie centuries or millennia ahead. Time dilation does not break the light speed limit. It reshapes the relationship between personal duration and external history, softening the subjective impact of great distances while preserving the absolute barrier against surpassing light itself. In this sense, the stretching of time joins the growth of effective mass as another layer of defense around the cosmic speed limit. As speed increases, the universe responds not only by demanding more energy for further acceleration, but also by altering how much existence can be fitted into a given journey. Clocks' slow lifetimes lengthen from the viewpoint of distant frames, and the very idea of before and after depends on who is watching. The speed of light thus asserts itself not only in how fast things move, but in how they age, how they endure, and how their histories are woven together across space-time. In the deep dark between stars where no air resists motion and no mountains rise to block a path, it might seem that once a craft begins to move, speed should come cheaply. A brief burst of thrust and then coasting forever feels like an efficient dream. On small scales within a planetary system, this picture holds enough truth to guide probes and orbiters along graceful trajectories. Yet when the target lies many light years away, and the goal is not merely to drift, but to approach a significant fraction of the speed of light, the quiet arithmetic of energy reveals a harsher reality. Every gain in speed carries a cost, and near the cosmic limit, that cost grows into something astronomically large. The starting point is simple kinetic energy, the energy of motion. In the calm world of low speeds, kinetic energy rises with the square of velocity and remains manageable. A small car, a fast aircraft, or a returning capsule all require energy that can be supplied by engines and fuels within human reach. Even a probe sent to the outer planets draws on chemical or gravitational energy that, while substantial, stays within the bounds of engineering. These familiar journeys depend on speeds that are tiny compared to the pace of light. As soon as the desired velocity reaches into tens of % of light speed, the classical formula begins to break down and relativistic energy takes its place. The total energy of a moving object, including its rest energy, grows with the Lorentz factor, that quiet number which swells as speed increases. For a modest test, imagine a compact interstellar craft with a mass of only 1 ton, a mere fraction of the mass of a present-day orbital station. To accelerate this small vehicle to 1/10 of the speed of light, the required kinetic energy, even in approximate classical terms, rises to a figure that dwarfs the yield of any conventional explosion. It corresponds to many hundreds of megatons of chemical or nuclear energy compressed into the motion of a single piece of hardware. In relativistic language, the energy content approaches the total annual consumption of a modern planetary civilization, all focused on moving one small craft to a speed that is still far below the cosmic limit. As the target speed increases, the numbers begin to climb, in a way that feels less like counting and more like ascending a steep slope. At half the speed of light, the relativistic correction becomes essential. The kinetic energy is no longer a simple multiple of the low speed case, it becomes many times larger. For the same 1-ton craft, the energy required reaches into ranges that rival the output of the central star intercepted over large areas and long times. The thought of building power systems capable of delivering such energy to a single vehicle, let alone doing so safely and repeatedly, stretches imagination. At 90% of light speed, the Lorentz factor has grown enough that the total energy of the craft, as seen from its original frame, is several times its rest energy. The kinetic portion of that total dominates. To supply this, a civilization would need to harness not just an advanced power grid, but a system comparable to planetary scale engineering, perhaps a shell of collectors encircling a star or vast structures occupying orbital space. Even then, this tremendous effort would propel only one small craft, and only for one journey. The price of speed is paid not only in raw energy, but also in the way that energy must be stored, directed, and managed. Rockets that carry their fuel must accelerate that fuel along with the payload. This coupling leads to a quiet but unforgiving relation known as the rocket equation. For every unit of speed gained, a certain fraction of the initial mass must be expended as reaction mass. To reach higher speeds, more fuel is needed. Yet that extra fuel itself must be accelerated, so further fuel is needed to push the earlier fuel, and so on. The relationship between desired final speed and required starting mass grows exponential. For modest missions within a planetary system, this exponential does not yet dominate. Ingenious staging and careful trajectory design keep fuel fractions within manageable limits. For relativistic missions, the curve hardens. To reach even a few tens of % of light speed with any rocket that carries its reaction mass, the starting mass may need to be many times the mass of the payload. At higher target velocities, the required mass ratio balloons to absurd figures where an entire asteroid or small moon would need to be converted into fuel to send a relatively tiny vessel outward. Relativity worsens this already severe trade-off. As speed increases, the effective inertia of the craft grows with the Lorentz factor, which means that each successive increment in velocity demands more thrust to produce the same change. More thrust requires more energy. The rocket equation quietly multiplies this burden by insisting that more energy also means more reaction mass to be accelerated. The circle tightens. Attempts to break free of chemical limitations lead to hypothetical systems with far greater specific energy. Nuclear fission, nuclear fusion, and matter-antimatter annihilation all promise on paper far better performance than any chemical propellant. In the most extreme case, a perfect matter-antimatter reaction converts essentially all mass into energy, maximizing the yield dictated by the relation between mass and energy discovered in relativity. Even here, the optimism fades under closer examination. To accelerate a 1-ton craft to 90% of light speed using such an almost perfect engine still demands quantities of fuel measured in many tons, and that fuel must be half matter and half antimatter. The antimatter, a substance that annihilates on contact with ordinary matter, would need to be produced at immense energetic cost and contained in elaborate magnetic traps with absolute reliability over long periods. A single failure would release energies comparable to global arsenals in an instant. Other proposals move the burden of energy away from the craft. Instead of carrying fuel, a sail might ride the pressure of light from lasers or from the star itself. In principle, this removes the rocket equation's tyranny over mass ratios because the reaction mass and energy source remain at home. Yet here the scale of power becomes daunting. A beam strong enough to push even a gram-scale sail to a significant fraction of light speed must deliver continuous power comparable to that of a large segment of a star's output over many minutes or hours. Construction of such an array demands megastructures in space while aiming and maintaining the beam over interstellar distances introduces its own set of severe challenges. For heavier craft carrying habitats and instruments, the power demands climb proportionally. No matter how the problem is framed, the same pattern emerges. As target speeds approach the speed of light, the energy required rises more quickly than intuition expects. For massive vessels, it soon surpasses any reasonable fraction of the total power that even a very advanced civilization might safely deploy. Attempting to accelerate many ships or to sustain regular traffic multiplies the problem until the dream resembles a project to tap entire stars as if they were mere engines. In this landscape, the speed of light appears again not just as a numerical ceiling, but as a summit surrounded by slopes that steepen relentlessly. The closer a planned journey comes to this summit, the more the cost of climbing it transforms from ambitious to absurd. Energy, which seemed at first to be a matter of engineering, reveals itself as another expression of the same geometric rule that binds mass motion and time together. The cosmic speed limit inscribes itself into the budget of any interstellar voyage, dictating not just what paths are possible, but which ones are remotely affordable, even for civilizations that might wield powers far beyond those of the present age. When the raw price of speed begins to loom over any realistic mission, imagination turns naturally toward better engines. If chemical propellants demand intolerable masses of fuel and still fall far short of relativistic flight, perhaps more exotic reactions can help. The logic seems clear. If each kilogram of propellant can release more energy, then each unit of reaction mass can push a craft further. Higher exhaust velocities should translate into higher final speeds with less fuel. In the language of idealized rockets, the change in speed that a vehicle can achieve depends on the speed at which it throws mass out the back, and on the ratio between its starting mass and its final mass after burning fuel. At first glance, this relation appears merciful. Doubling the exhaust velocity roughly doubles the change in speed accessible for a given fuel fraction. Designing an engine that can hurl exhaust at tens or hundreds of kilometers per second seems like a promising route away from chemical limitations. Nuclear options step into this picture. Fission releases far more energy per unit mass than chemical reactions, suggesting exhaust streams that could leave a vehicle at tens of kilometers per second rather than single digits. Fusion, which taps the binding energy of light nuclei, promises even more. In principle, a well-designed fusion engine might expel reaction products at a significant fraction of light speed. Matter-antimatter annihilation lies at the extreme end of this spectrum. In a nearly perfect reaction, the entire rest mass of the fuel becomes energy, much of it emerging as high-energy photons. A rocket that directs this radiation backward as exhaust would, in theory, enjoy the highest possible exhaust velocity approaching the cosmic limit itself. In idealized form, this is the photon rocket, a vehicle that recoils from beams of light it emits, carrying no exhaust heavier than radiation. However, the same relation that encourages higher exhaust velocities also hides a quiet trap. The change in speed depends on the logarithm of the mass ratio, the initial mass divided by the final mass. This means that to gain additional speed, the ratio must grow exponentially. Each extra increment in target velocity requires the starting mass to swell by a factor that soon becomes huge. Even when the exhaust velocity is very high, the curve does not flatten into an easy path. Instead, it turns into a steep ramp where more and more initial mass must be committed as reaction mass to add ever smaller increments of possible speed. For a chemical rocket, this pattern reveals itself quickly. A relatively modest target speed already demands that most of the vehicle be fuel. For a nuclear thermal rocket using fission, the curve is somewhat kinder. A larger fraction of the vehicle can remain as payload for the same change in speed. Yet when the desired delta grows to a substantial fraction of light speed, the exponential law reasserts itself. The initial mass required to accelerate a given payload to such speeds and then decelerate it again at the destination climbs into absurd territory, even if the engine is far more efficient than anything built so far. Fusion and antimatter improve the specific energy dramatically, but they do not erase the structure of the relation. A fusion rocket can in principle reach higher speeds for a given mass ratio than a chemical or fission design because its exhaust leaves faster. Nevertheless, if the mission demands a cycle of acceleration, cruising, and deceleration near relativistic speeds, the starting mass still needs to be many times the final payload. When antimatter drives enter the picture with exhaust velocities approaching the speed of light itself, the numbers shrink but do not collapse into comfort. The total fuel mass required for a round trip to a nearby star at a large fraction of light speed may fall into the range of tens of tons for a ton-scale payload, which sounds manageable until the engineering realities appear. Producing that much antimatter would require energy budgets that rival those of entire planets, and storing it would demand containment systems of unprecedented perfection. A single fault would unleash the entire stored energy at once. Staging offers a partial workaround. By discarding empty tanks and engine modules along the way, a multi-stage rocket can mimic in serial fashion what would otherwise be an impossible single step in mass ratio. Each stage accelerates the next, then is abandoned as spent mass, leaving less weight for later stages to push. This technique has enabled high performance within planetary systems, but when it is extended to relativistic ambitions, it leads to daunting architectures. A hypothetical multi-stage interstellar vehicle might begin its journey as a structure far larger than any present-day station, only to arrive as a modest core after jettisoning layer upon layer of empty shells. Beyond a certain point, the extra complexity and initial mass cease to look like clever design and begin to resemble a slow collapse under the weight of the exponential relation itself. To escape the need to accelerate, fuel concepts emerge that push the responsibility outward. Beamed propulsion imagines a vehicle that unfurls a reflective sail and rides the pressure of light from an external source. Lasers or microwave emitters anchored near a star pour energy into a narrow beam aimed at the sail. In principle, this allows the craft to gain speed without carrying its own reaction mass, sidestepping the rocket equation's harsh growth in mass ratio. Yet the cosmic limit finds a way into this picture as well. Diffraction ensures that any beam, no matter how well collimated, spreads over distance. To keep enough power concentrated on a sail many astronomical units away, the transmitter must be enormous. Arrays of mirrors or antennas with sizes rivaling planets would be needed to support truly relativistic missions, and the power fed into them would have to be sustained at extraordinary levels. The engineering burden moves from fuel tanks to megastructures, but the underlying cost in energy and infrastructure remains extreme. Concepts like the Bussard ramjet push farther into ingenuity. In this vision, a craft deploys a vast electromagnetic scoop that gathers thin interstellar hydrogen and feeds it into a fusion reactor. The vehicle thus harvests fuel as it flies, freeing itself from the need to carry reaction mass from home. However, the interstellar medium is thin. The scoop must be enormous to gather sufficient mass, and at high speeds the oncoming hydrogen behaves less like free fuel and more like a stream of energetic particles. The drag created by deflecting this inflow can match or exceed the thrust produced by burning it. Detailed analyses suggest that beyond a certain velocity the ramjet would be braked more than it is driven. Once again, the cosmic speed limit and the realities of energy conspire to cap performance. Across all these possibilities, a pattern emerges. Each new propulsion scheme pushes the boundary of what seems achievable, improving the situation on one front while revealing hard limits on another. Chemical engines give way to nuclear to fusion to annihilation, rockets to sails and ram scoops, yet the same diminishing returns return. Exhaust can be hurled faster, beams can be made brighter, scoops can be made wider, but the exponential law of mass ratio, the finite energy of any star, and the resistance of space-time to near light speed motion weave together into a combined constraint. Underneath the same geometry rules, the speed of light draws a line on every performance chart and every propulsion equation, and as designs reach toward that line, required resources climb steeply. Rockets and exotic drives do not rewrite this reality. They simply trace different paths into the same narrowing corner where the dream of effortless relativistic travel fades into a recognition of just how tightly the universe holds to its chosen limit. In the sparse medium between stars, the phrase empty space is more a convenience than an accurate description. Even far from any sun or planet, the interstellar environment contains stray atoms, grains of dust, and a faint bath of radiation left over from ancient processes. For a slow-moving craft, these traces hardly matter. A few atoms of hydrogen per cubic centimeter drift past without leaving a mark, and specks of dust rarely strike with enough energy to do more than pit a surface. At ordinary velocities, the void lives up to its quiet reputation. The picture changes when speed climbs toward a significant fraction of the speed of light. In that regime, every encounter with the tenuous medium becomes a violent event. From the viewpoint of the craft, the surrounding gas no longer drifts lazily. It approaches in a fierce headwind at relativistic speed, and the humble hydrogen proton turns into a projectile carrying as much energy as macroscopic objects at lower speeds. Collisions that would once have been negligible now resemble impacts from cosmic bullets. A single proton that strikes the forward shield at 99% of light speed delivers energy concentrated into a volume far smaller than a grain of sand. The kinetic energy of such a particle, scaled by the Lorentz factor, rivals that of a thrown ball, yet it is deposited into a microscopic region of material. Cascades of secondary particles burrow into the structure, knocking atoms from their places and leaving behind tiny zones of damage. Multiply this event by trillions of protons passing through each square meter of frontal area every second, and the gentle drizzle of interstellar hydrogen becomes a storm of radiation. The surface facing forward must absorb or deflect a barrage of high-energy particles, each one contributing a little to heating, erosion, and activation. Over time, the material grows embrittled and radioactive. Electronics behind the shield experience a shower of secondary particles that flip bits and gradually undermine reliability. Life forms, if any are present, face a bath of ionizing radiation so intense that unprotected tissues would fail within moments. The same relativistic transformation affects dust. Small grains, perhaps a micron in size, float harmlessly through the medium at low relative speeds. At 90% of the speed of light, each such grain becomes a destructive missile. When it collides with the hull, the energy released is comparable to that of an explosive detonating in a tiny volume. Material in the impact zone vaporizes, shock waves propagate through the structure, and fragments fly outward as high-velocity shrapnel. A single encounter might perforate a critical subsystem. A sustained journey would almost certainly experience many such impacts, unless the density of dust along the path were extraordinarily low. Shielding strategies struggle in the face of these conditions. A block of material at the bow can absorb many hits, but it must be thick enough to stop cascades of particles and sturdy enough to endure repeated explosive events. As the thickness increases, so does mass, and every extra ton must be accelerated along with the payload feeding back into the energy problem. A shield made of water or ice might help by spreading and absorbing heat, but it too would erode under the barrage, requiring either replenishment or an initially large reserve. Electromagnetic shields offer partial relief. Strong magnetic fields extending ahead of the craft can deflect charged particles, bending their paths away before they strike. In principle, such a magnetic bubble could push aside a substantial fraction of the incoming proton flux. Yet neutral atoms and dust grains do not respond as easily. Some designs imagine ionizing the gas in front of the craft with a directed beam, then steering the newly charged particles with fields. In every case, the price is complexity and power. Generating and sustaining fields strong enough to carve out a protective cavity at relativistic speeds demands significant energy and equipment. The interstellar radiation field adds another layer of hazard. The background glow of the universe, composed of low-energy photons, seems harmless to a slow observer. At near light speed, the Doppler effect compresses this radiation into higher frequencies in the direction of motion. Photons that were once mild microwaves can shift into the ultraviolet or even into the X-ray band as they stream toward the craft. The combined effect of boosted background light and oncoming gas forms a radiative wall, a region where the environment becomes so hostile that survival demands heavy protection. As speed increases, this wall thickens. At some fraction of light speed beyond which the exact value depends on shielding and risk, it becomes impractical to prevent serious damage. A vehicle without extraordinary defenses would simply erode heat and disintegrate under the relentless flux. In this way, the interstellar medium, which seems so forgiving to slow travelers, becomes one more agent enforcing the cosmic limit on speed. The faster a craft tries to go, the more it transforms the space ahead into a concentrated beam of destructive particles and radiation. The universe appears to respond to each attempt to close the gap with light speed by turning the path itself into an obstacle. Any realistic design for near light speed travel must carry or generate enough shielding to withstand an environment that grows harsher with every increase in speed, yet every kilogram devoted to protection adds to the mass that must be accelerated. In this balance, the interstellar medium reveals itself as an active participant in the drama of high-velocity motion, quietly transforming into a storm whenever a massive object rushes too close to the speed of light. At modest speeds, the universe presents a familiar face. Stars dot the sky in every direction, their light spread roughly evenly across the celestial sphere. The soft band of a spiral galaxy arches overhead, and constellations hold their shapes for generations. For a world confined to slow motion, this view appears permanent and objective. The relativistic structure of space-time quietly contradicts that comfort. As velocity rises toward a large fraction of the speed of light, the appearance of the sky begins to bend. Directions compress, colors shift, and brightness redistributes until the panorama becomes something different. The change starts when a craft increases its speed along some chosen direction. Even at a few tenths of light speed, an effect known as aberration begins to funnel the light from ahead into a narrower cone. Photons that once arrived from a wide spread of angles are in the craft's frame tilted forward. The apparent positions of stars shift toward the direction of motion. Behind the craft, the opposite happens. The light is dragged away from the line of sight, and the rearward dome grows emptier. At higher speeds, this focusing becomes dramatic. At 90% of the speed of light, most of the visible stars seem to cluster in front of the trajectory. This geometric concentration of starlight comes with a shift in frequency. Because of the relativistic Doppler effect, light from the forward hemisphere does not only arrive from altered directions, it also arrives bluer and more energetic. Yellow stars appear whiter while white stars drift into blue. Radiation that began in the ultraviolet can move into the X-ray band. Behind the craft, the opposite takes place. Wavelengths stretch. Blue stars soften toward white, then yellow, then red. Visible light lengthens into infrared and beyond. The rearward universe cools and dims, sliding out of ordinary sight. At extreme velocities, these tendencies reinforce one another. The forward view narrows into a bright eye of concentrated radiation, a patch of sky that holds much of the visible structure of the cosmos. Within this cone, brightness is amplified both by geometric focusing and by the blue shift that drives photons to higher energies. The background glow of the universe becomes a hotter field in the direction of motion. At the same time, the sky to the sides and rear fades almost to black. Stars that once formed patterns of orientation become too red and too faint to detect. From the frame of the fast-moving craft, the universe resembles a tunnel with a tightening mouth ahead and darkness closing in behind. This pattern is not merely aesthetic. The same beaming that brightens the forward sky also concentrates hazardous radiation. Cosmic rays and background photons are driven into a narrower frontward cone, raising the energy flux that strikes whatever shield protects the vessel. Protective systems must therefore work hardest along a shrinking area while the rest of the hull lies in relative shadow. The high-energy character of the forward light field reinforces the notion of a radiative wall that thickens with speed. The geometry that allows all observers to measure the same speed of light conspires to make the view ahead harsh and dangerous. Relativistic aberration and Doppler shift also alter the perception of motion through large-scale structures. A journey toward the center of a galaxy at high speed would not resemble a simple fall inward through a familiar star field. Instead, the core's dense region of stars would appear further concentrated and brightened along the line of travel, while spiral arms and outer regions would slip away behind in a fading red haze. The sense of moving through a balanced disk of light would give way to an impression of chasing a distant beacon through an otherwise deepening void. Even the cosmic microwave background, the nearly uniform afterglow of the early universe, obeys this pattern. In a frame moving rapidly relative to this background, the glow is no longer the same in all directions. It becomes hotter and brighter ahead and cooler behind, forming a dip in the sky's temperature that encodes the craft's motion with respect to the large-scale fabric of the cosmos. This effect already appears in the motion of galaxies and clusters which drift through the background at modest fractions of light speed. A truly relativistic vehicle would amplify the pattern into an extreme contrast with the forward glow, compressed into much higher frequencies. All these visual and radiative distortions arise from the same mathematical structure that enforces the light speed limit. The Lorentz transformations that keep the speed of light constant for every inertial frame also dictate how angles, frequencies, and intensities must change between frames in relative motion. They leave no room for a single universal sky. Each high-speed observer inherits a different map of directions and colors, all consistent with the same underlying events. The closer a trajectory comes to the cosmic limit, the more aggressively space-time reshuffles the appearance of the universe to protect that limit. The dream of gliding through a stable sea of stars thus meets another quiet boundary. Even if a craft could obtain the immense energy required and endure the physical hazards of near light speed flight, the view outside would no longer resemble the familiar field of constellations. The cosmos would present itself as compressed brilliance ahead and almost empty darkness behind, a reminder that high velocity does not simply shrink distances. It rewrites how space is seen in a way that never allows any observer with mass to forget how close the path has come to the speed of light. When every ordinary route toward the light speed limit ends in infinite energy and destructive radiation, imagination turns to a different strategy. Instead of forcing matter with mass to move faster through space, perhaps space itself can be reshaped so that distant places slide closer together. General relativity already shows that space-time is flexible. The fabric of the cosmos expands, separating far galaxies. Near heavy bodies, it curves, bending light and slowing clocks. In those examples, nothing locally outruns light, yet distances between faraway points change with time. If geometry can stretch on its own, perhaps a carefully sculpted patch of geometry can be turned into a vessel. In this vision, a craft rests inside a small region of nearly flat space-time, while the region just behind it expands and the region just ahead contracts. The whole pocket, often called a warp bubble, rides this wave of curvature. To distant observers, the bubble can cross many light years in less time than light would need to traverse the same coordinate distance. Inside, no object or signal ever exceeds light speed relative to its immediate surroundings. On paper, the cosmic limit remains intact, even though the effective trip is superluminal. The mathematics describing such a bubble are precise. Space in front is compressed, reducing the proper distance to a destination, while space behind is stretched, increasing the distance back to the starting point. Within the bubble, the metric is almost flat, and an observer at its center feels no acceleration. The entire effect resides in the way space-time bends in a thin shell around the bubble. There the difficulty becomes clear. Ordinary matter and radiation always have non-negative energy density. They curve space-time in the familiar way associated with attraction and collapse. A warp bubble, by contrast, requires regions where the effective energy density is negative, producing a kind of repulsive curvature. Negative energy is not entirely unknown. Quantum field theory predicts small regions where the energy dips below that of empty space, for example, between closely spaced conducting plates. But these quantum effects are tiny and do not resemble a stable macroscopic halo of exotic matter that could be wrapped around a ship. Early estimates suggested that a warp bubble big enough to enclose even a modest vehicle would require exotic energy comparable to converting a giant planet entirely into mass energy. Later refinements, which alter the bubble's shape and redistribute the stresses, reduce the total somewhat, but not to comfortable values. They must avoid instabilities. If the supporting configuration is easily disturbed, small fluctuations in the exotic field may grow and destroy the structure. Other problems arise when control is considered. Signals inside the bubble cannot travel faster than light to reach its leading edge, yet that edge is what must respond if the bubble is to turn or to slow down. In many treatments, the front boundary lies outside the future light cone of interior events. Instructions sent from the center can never arrive in time to influence the geometry ahead. The bubble then behaves more like a current in space-time that carries its occupant passively than like a vehicle that can be steered. Some studies indicate that radiation from the region in front would accumulate along the leading edge compressed there by the same curvature that drives the bubble forward. When the warp field collapses, this stored energy could be released in a burst of high-energy particles and photons at the destination. A related family of ideas replaces moving bubbles with fixed tunnels. General relativity admits solutions in which two distant regions of space-time are joined by a throat creating a wormhole. To an external observer, the mouths of a wormhole might lie many light years apart. To a traveler who enters one mouth, passes through the throat, and exits the other, the internal distance could be very small. Once again, no local rule about light is broken. Light still takes years to cross the external distance between the mouths, while the journey inside might last minutes. Yet traversable wormholes share the same essential difficulty as warp bubbles. To hold a throat open wide enough and long enough for passage, the stress energy supporting it must include negative energy density. Without this exotic support, gravity forces the tunnel to pinch off into a black hole before anything crosses. Quantum fields can produce tiny negative energies, but no known mechanism scales them into macroscopic scaffolds. If one mouth is accelerated or moved into a different gravitational potential, time at that mouth runs at a different rate from time at the other. In some arrangements, this allows closed time-like curves paths through space-time that return to their own past. Many researchers suspect that a full quantum theory of gravity not yet known will enforce a kind of chronology protection that forbids these configurations or makes them violently unstable. Taken together, warp bubbles and wormholes illustrate how generous and how strict the laws of space-time can be. On one level, the equations of general relativity admit geometries that seem to offer shortcuts around the light speed limit. On another level, those same equations demand forms of matter and control that lie far beyond anything that appears in nature. Large persistent negative energy, precise manipulation of curvature, and safe handling of compressed radiation may be as unreachable as infinite fuel. In that sense, the most alluring apparent loopholes end up reinforcing the original rule. Geometry itself can move in surprising ways, yet wherever realistic physics is imposed, the speed of light still stands as a boundary between what can be drawn on paper and what the universe will actually allow to unfold. In the long search for ways around the cosmic speed limit, a certain mathematical shadow begins to appear at the edge of the equations. Relativity forbids particles with mass from accelerating up to light speed, and it binds massless entities such as photons to travel exactly at that speed. Between these two regimes, the rules leave no gap, yet on paper there is another stranger category, hypothetical particles that would always move faster than light. These entities receive a name derived from the word for swiftness, and in theory they inhabit a domain beyond the reach of ordinary matter. The starting point lies in the same expression that ties energy, momentum, and mass together. For ordinary particles, the mass term is positive. As speed increases, the total energy grows and the velocity approaches the speed of light from below but never reaches it. If in a purely formal way that mass term is allowed to become negative in its square, the expression still maintains internal consistency, but its implications change. The resulting entity can never slow down to light speed. Its allowed velocities reside entirely above the limit, not below. The mathematics suggests a mirror world in which higher energies correspond to lower speeds, and in which an attempt to rob such a particle of energy drives it closer to infinite velocity. In this mirror realm, particles that always outrun light are called tachyons. They do not merely exceed the speed limit, they are constrained to remain superluminal. Just as no finite push can drive an ordinary particle to light speed, no finite braking can slow a tachyon down to that boundary. The two categories remain separated by the same geometric wall. However, this formal symmetry conceals a deep problem. If a particle can travel faster than light, then in certain frames it must be seen as moving backward in time. Relativity already allows observers in different states of motion to disagree about the order of events that are not causally linked. With tachyons in the mix, even events that do influence one another can be arranged in contradictory sequences. A signal sent by a tachyon from one location to another could in some frames arrive before it was emitted. By combining such signals in cleverly arranged loops of relative motion, a pair of devices might apparently exchange messages with their own past. The simple image is that of a signaling device that sends a superluminal pulse to a distant receiver, which then immediately responds with its own faster-than-light emission. In one frame, the sequence runs comfortably forward: emission, reception, reply, second reception. In another equally valid frame, the second reception occurs before the first emission, granting advance knowledge of an action that has not yet been taken. With more intricate arrangements, a chain of superluminal communications can be built that leads back to the origin, creating a closed loop in time. In such scenarios, paradox rises from the mathematics. A machine might be instructed to destroy itself before sending a particular signal, yet the signal is needed to trigger the act of destruction. If the machine succeeds, the signal is never sent. If the signal is not sent, the machine survives, ensuring that it will eventually send it. The world line of the device attempts to occupy mutually incompatible histories. The consistency of cause and effect which relativity protects as long as no influence outruns light begins to fray. For this reason, theoretical treatments of tachyons typically regard them as signs of instability rather than as real propagating entities. In quantum field theory, a field with a tachyonic mass term does not describe particles that actually travel faster than light. Instead, it signals that the assumed vacuum is not the true lowest energy state. The field wants to roll down to a different configuration where the negative mass squared disappears, restoring ordinary subluminal excitations. In that interpretation, tachyons are not inhabitants of nature, but warnings that a particular description has chosen the wrong ground. Experimental searches add further weight to the suspicion that such faster-than-light particles do not exist as stable propagating objects. High-energy cosmic rays, accelerator beams, and delicate timing experiments all offer opportunities for superluminal effects to appear. None has provided convincing evidence. On rare occasions, measurements have seemed to hint at particles arriving slightly earlier than light would, but each such case has been traced to errors in instrumentation, calibration, or analysis. One prominent example involved neutrinos sent through Earth between two laboratories. Early reports suggested that the particles had arrived a tiny fraction of a second too soon, which, if true, would have forced a drastic revision of fundamental physics. Careful re-examination uncovered faulty connections and clock issues. Once corrected, the neutrinos behaved exactly as expected, traveling at or just below the light speed limit. Even without direct observation, broader considerations argue against the existence of real faster-than-light particles. The second law of thermodynamics, which states that entropy tends to increase in isolated systems, would be jeopardized if signals could move backward in time. Devices could in principle send instructions into their own pasts to reorganize systems, reduce disorder, and extract work without a corresponding cost, undermining the arrow of time that underlies everyday experience. The stability of the vacuum also comes into play. A world populated by freely propagating tachyons would allow processes in which lower energy configurations are endlessly undercut by ever more extreme superluminal states leading to runaway behavior. The observed calm and longevity of cosmic structures suggests that such instabilities are absent. In all of these arguments, the same theme reappears. Relativity's equations can be extended formally into regions that describe speeds greater than light, but the attempt to promote those formal solutions into physical objects tends to break the logical and thermodynamic structure of the universe. Rather than welcoming tachyons as residents of a hidden sector, most treatments interpret them as invitations to refine models until the ghostly terms disappear. The light speed limit, which at first glance appears merely as a kinematic boundary between slow and fast, is thus revealed as a safeguard for causality and consistency. Allowing influences to cross that boundary undermines the order of events, invites paradox, and disrupts the foundations of statistical physics. In contrast, a universe where every real particle either travels below light speed or, if massless exactly at that speed, remains coherent. In such a cosmos, different observers may disagree about simultaneity and may assign different durations to the same journey, yet they can all agree on which events can influence which. The exclusion of tachyons is not an arbitrary rule layered on top of relativity, but an almost inevitable consequence of insisting that cause precede effect along every possible world line. By exploring the idea of faster-than-light particles and finding them incompatible with the observed stability and logic of the universe, physics circles back to the original boundary with renewed confidence. The very attempts to imagine entities that outrun light reinforce the conclusion that the limit is not an accident of current understanding, but a deep property of the space-time in which all real events unfold. In the domain of the very small, where atoms, electrons, and fields replace planets and rockets, the rules of behavior seem at first to loosen. Particles appear in more than one place at once, pass through barriers that classical reasoning would label impenetrable, and influence one another instantly across distance. It is natural to wonder whether this microscopic strangeness might conceal some route around the speed of light limit that blocks macroscopic travel. If quantum events are not bound by ordinary notions of locality, perhaps information or even matter can be transferred faster than light by exploiting their peculiar connections. Modern quantum theory answers this hope gently but firmly. The strangeness is real, yet it does not open the kind of passage that would allow signals to outrun light. One of the most striking features of quantum mechanics is entanglement. When two particles emerge from the same interaction, their properties can be correlated in a way that defies classical explanation. A measurement on one immediately fixes the outcome of a corresponding measurement on the other, no matter how far apart the pair may drift. In thought experiments and real laboratories, pairs of photons or electrons are prepared in such linked states, then separated by distances ranging from meters to kilometers and beyond. When one member of the pair is examined, the result is random, but instantly determines the state of its partner. This instantaneous correlation seems at first glance to violate any notion of a finite signal speed. Yet a closer look reveals that no usable message is transmitted. The outcome of each measurement is unpredictable. An experimenter who examines one particle sees only a series of random results. The correlations emerge only when records from both sides are later brought together and compared, a process that always proceeds at or below the speed of light. The entangled link does not carry commands, it simply ensures consistency between outcomes when they are eventually reconciled. Another quantum phenomenon that attracts attention is tunneling. In classical terms, a particle confronting a barrier higher than its energy cannot pass. In the quantum picture, the particle is described by a wave function that extends into and beyond the barrier. There is a calculable probability that the particle will be found on the far side, as if it had passed through by a route unavailable to classical intuition. Some measurements of tunneling times have led to claims that the effective speed associated with the process exceeds the speed of light. Detailed analysis shows that no portion of the wave front or any actual signal crosses the barrier superluminally. Instead, the shape of the wave and the definition of traversal time lead to apparent velocities that are not connected to the transport of information or energy. Once again, the weirdness of the effect does not translate into a mechanism for faster-than-light communication. Beneath these specific examples lies a more general structure. Quantum field theory, which combines the probabilistic rules of quantum mechanics with the space-time geometry of special relativity, demands that field operators at space-like separated points commute. This technical requirement enforces the rule that no measurement performed in one region can influence the statistics of results in another region that lies outside its light cone. Correlations may exist, but no controllable change at one point can be used to transmit a signal to the other faster than light. The mathematical framework is built so that causality is preserved even while non-local correlations flourish. When new fields are introduced, they must respect the same constraints if they are to describe stable physical systems. The interplay between quantum uncertainty and relativistic structure also limits how sharply packets of energy or matter can be localized without creating conditions that collapse into other forms. Efforts to confine a particle beyond a certain point inject enough energy into a region that particle-antiparticle pairs can be created, blurring any attempt to track a single entity at arbitrarily fine resolution. This softens dreams of microscopic couriers that could somehow slip between the meshes of light cones and carry messages through a hidden substructure. The very act of sharpening position or energy beyond quantum limits reshapes the system into something different. Experimental tests of quantum non-locality strengthen the sense that the universe is both more connected and more constrained than classical pictures allow. Violations of inequalities that any local hidden variable theory would obey confirm that entangled correlations cannot be explained by pre-existing shared instructions. At the same time, every such test has respected the relativistic bound on signal speed. Detectors separated by large distances record outcomes whose correlations defy classical expectations, yet no observer can use those correlations alone without later comparison to send a chosen bit of information across the gap faster than light. In this quiet collaboration between quantum theory and relativity, the speed of light emerges not as a clumsy external limit bolted onto a world of otherwise free motion, but as a fundamental feature of how influences propagate at every scale. Quantum fields fluctuate and intertwine, entanglement weaves connections through space, and tunneling allows particles to appear where classical trajectories would forbid them. Throughout, the light cone structure of spacetime remains intact. Non-local correlations coexist with strict causal order, forming a universe where strangeness is allowed, but true superluminal signaling is not. The microscopic realm, far from undermining the cosmic speed limit, reinforces it in a deeper language, showing that even where intuition struggles, the boundary set by light still shapes what can and cannot occur. On the scale of a single world, the light speed limit feels distant. Signals circle a planet in fractions of a second, aircraft cross continents in hours, and data glides through networks so quickly that delays are counted in tiny slices of time. Within this sphere, a civilization can imagine that distance has been conquered. Messages arrive almost instantly, travel times shrink, and the idea of a truly unreachable place fades. The larger stage of the galaxy returns that sense of reach to its proper size. Distances measured in light years are not simply greater, they belong to a different regime. Even if a future society masters engines that push craft to a tenth or a fifth of the speed of light, journeys to nearby stars still take decades. Communication between such missions and their origin worlds carries delays that shape every decision. A message sent to a vessel 10 light years away arrives after a decade, and any reply requires another decade to return. Coordination across such spans becomes less like conversation and more like correspondence between different eras. As ambitions stretch beyond the closest stellar neighbors, the pattern grows more extreme. Traveling to a system 100 light years away at a tenth of light speed requires roughly 1,000 years in the frame of the origin. By the time such a mission arrives, the civilization that launched it may have changed beyond recognition or ceased to exist. Any form of real-time control or shared culture across such distances dissolves. Colonies founded around distant suns must evolve into independent societies shaped by their local environments rather than by close guidance from their origin. On larger scales, the galaxy itself becomes a landscape of isolation. A spiral disk may hold hundreds of billions of stars scattered across 100,000 light years, yet most of them remain forever remote. Even if automated probes are dispatched in large numbers, their arrivals and their reports stream back across periods comparable to geological epochs, so expansion across such a disk resembles a slow diffusion with each outpost developing along its own trajectory. This picture ties into the puzzle often called the Fermi paradox, the question of why in a universe so large and apparently hospitable to stars and planets, signs of other civilizations are not obvious. If technological societies were able to cross a galaxy quickly leaving artifacts and beacons in their wake, then a young species turning its instruments outward might expect to find clear traces. The light speed limit alters that expectation. If every civilization is bound to subluminal speeds, then the time needed to fill a galaxy, even with self-replicating machines, becomes comparable to or greater than the lifetimes of stars and cultures. Civilizations may flare into existence, send out a few emissaries to nearby systems, then falter or transform before their influence reaches far. Their signals attenuate, their probes fall silent, and their engineering works erode under cosmic processes. To a later observer arising elsewhere, the galaxy may appear quiet even if many such episodes have unfolded in the deep past. Beyond the galaxy, the constraints sharpen further. The space between galaxies is far wider than that between stars, and the expansion of the universe adds its own moving boundary. Distant galaxies recede so quickly due to cosmic expansion that their light never reaches a given observer. They reside beyond a horizon set not by engineering but by the dynamics of spacetime itself. A single galaxy, or at most a small cluster of gravitationally bound neighbors, becomes the effective arena in which any species can act. Everything beyond is visible only as ancient light. Within that arena, the light speed limit also shapes the inner dynamics of a technological species. The maximum rate at which information can be moved between 2 points, even with perfect infrastructure, is capped. Large societies must adapt to the fact that decisions and knowledge cannot be distributed instantaneously across planetary, let alone interstellar scales. Political structures, scientific collaborations, and cultural exchanges must build this finite speed into their design. Attempts to impose uniform rapid control over far-flung regions encounter a simple barrier signals cannot outrun light, and every extra kilometer adds delay. In practice, this encourages a degree of localization. Planetary networks may remain tightly knit, but interplanetary and interstellar relations become looser based on shared frameworks and long-term agreements rather than real-time oversight. Over long periods, the same constraint may become a source of quiet stability. If no civilization can rapidly overwhelm another across light years, then interactions at those distances are inherently slow. Conflicts cannot escalate instantaneously on interstellar scales because fleets and signals alike are bound by the same finite speeds. A slow universe is not necessarily a peaceful one, but it is one where large-scale events unfold over spans long enough for adaptation. In this way, life in a slow civilization is framed by the light speed limit at every level. Exploration proceeds, but in decades and centuries rather than days. Communication flourishes locally, yet stretches into long silence across the stars. Ambitions reach outward, but always encounter distances that do not compress as easily as earlier barriers have, Within those limits, knowledge deepens about the local star and the nearby planets. The unreachable vastness beyond does not diminish what can be understood and shaped close at hand. It provides a backdrop of scale against which the achievements of a species confined to its finite region take on a different kind of significance, not as steps toward total conquest, but as intricate arrangements of life and awareness within a universe that will always remain mostly out of reach. In the final shape of the story, the light speed limit stands not only as a technical boundary, but as part of the background against which any civilization defines itself. Horizons that are first the next valley or the far side of the sea slowly expand until the local sky becomes a navigable dome. When instruments extend sight into radio waves and X-rays, the universe reveals itself as a structure so large that no vessel of wood or metal can hope to span it. The same equations that describe this vastness also quietly fix the maximum pace at which cause and effect can travel. 300,000 kilometers per second becomes both an enabler and a constraint, allowing information to cross planetary orbits quickly enough for coherent societies to form while freezing distant galaxies into images that can never be visited. In this landscape, meaning does not arise from conquering the whole, but from the depth with which a finite region is inhabited and understood. A civilization that recognizes the light speed barrier can still fill its local system with observation platforms, habitats, and networks of sensors. Moons, asteroids, and artificial stations become beads on threads of activity that loop around a central star. Long-range telescopes watch supernovae in distant galaxies and trace fluctuations in the cosmic background glow that preserve imprints of the earliest times. None of these endeavors require outrunning light. They turn the limit into a frame within which exploration unfolds inwardly rather than outwardly without bound. Over millennia, such a civilization might seed nearby stars with semi-relativistic probes. Each tiny vehicle carries instruments, archives, and machines capable of constructing new outposts on arrival. The journeys take decades or centuries in the frame of origin, but they remain bound by the same finite speed. When the first data streams drift back across the light years, they arrive as messages from the past. Decisions about further missions or eventual settlement are made in the knowledge that feedback is slow and that local autonomy at each destination is inevitable. In this way, the cosmic limit shapes not only travel but the structure of thought and governance. The barrier also shapes expectations about company in the universe. If no civilization can cheaply or quickly cross the interstellar gulfs, then most intelligent species that arise will remain isolated to some degree. Their radio emissions fade with distance. Their beacons blend with the glare of their stars. A signal detected on one world from an origin hundreds of light years away carries with it an inherent delay. By the time it is noticed, decoded, and answered, the sender's civilization may already be centuries older or gone entirely. Mutual dialogue becomes difficult, yet the existence of such a signal would confirm that the story of confronting the light speed limit is not unique. Other minds under other suns trace similar arcs of discovery meeting the same boundary from different directions. On a more intimate scale, the limit quietly influences the inner experience of time. No single conscious being can outlive the light travel time across a galaxy, and no chain of generations can erase the fact that information takes a fixed interval to cross a given gap. Plans that reach across systems and centuries must be framed as open-ended intentions rather than exact scripts. Some seeds arrive, some messages are read, and some projects are completed by descendants who inherit only the outline of their originator's motives. The universe's refusal to allow instantaneous connection makes room for this layered succession. From another angle, the boundary encourages certain forms of attention. If the vast majority of stars and galaxies will never be visited, then the local star, its planets, and the few dozen neighboring systems become singularly important. Their histories, climates, geological records, and potential for life offer a richness that does not diminish just because the wider cosmos remains distant. A study of one planetary atmosphere, one deep ocean, or one subsurface sea carries as much wonder as the survey of a cluster of galaxies. The limit of light speed ensures that these close-by mysteries cannot be casually discarded in favor of more spectacular but unreachable targets. In the end, the cosmic speed limit appears less as an arbitrary prohibition and more as a contour in the landscape of possibility. Within that contour, complexity, awareness, and culture still flourish. Stars are understood, planets are tended, and local space is woven into intricate environments where life and technology interact. The equations that prevent a ship from ever reaching light speed are the same ones that allow stable atoms, long-lived stars, and a predictable flow of cause and effect. The boundary that denies certain journeys is entangled with the structures that make any journey and any observer possible. Seen in this light, the dream of traveling faster than photons becomes less central. The wonder shifts from the idea of spanning everything to the realization that even a small neighborhood of space-time explored within the speed limit offers more than any single civilization can exhaust. The night sky remains a map of unreachable places, yet each point of light continues to send stories that arrive at the only rate the universe permits. Within that steady rain of delayed information, minds that accept their slowness still trace patterns and feel the quiet pull of mysteries they will never directly touch. The speed of light thus becomes both a wall and a rhythm, setting the pace at which the universe reveals itself and at which any species may learn its place within the cosmic web.